Welcome back to our class, Algorithms and Data Structures. This will be the last in a series of lectures that are talking about sorting. And so we've gave an introduction, talked about faster sorting methods, had a couple different Java interludes that were related. And this lecture will be focusing on sorted lists. So with that, here is the textbook chapter contents. And for some orientation, chapter 10 introduced you to the ADT list. The entries in a list are ordered simply by their positions within the list. Thus, a list has a first entry, a second entry, and so on. This ADT enables you to order entries according to any criterion you want, alphabetical or chronological, for instance. In fact, chapter 10 shows you an example that used a list to organize names in alphabetical order. To do so, the client had to determine where in the list a particular entry belonged. If your application creates a list and then at some point needs to sort the list entries into numerical or alphabetical order, for example, you can add a sort operation to the ADT list. You can use one of the algorithms given in chapters 15 and 16 to implement this operation. But when your application requires only sorted data, having an ADT that orders that data for you would be more convenient than the ADT list. The sort list is such an ADT. When you either add an entry to or remove an entry from a sorted list, you provide only the entry. You do not specify where in the list the entry belongs or exists. The ADT decides this for you. So this chapter will describe the operations of the ADT sorted list, provides examples of using a sorted list, and presents two possible Java implementations. One of these implementations uses the ADT list, but if it is not especially efficient. Chapter 18 addresses the reuse of a class and provides a more efficient implementation of the sorted list as it discusses the use of inheritance. What then can we say, what can you place in a sorted list? One possibility is strings, since the class string provides a compare to method for comparing two strings. In general, you can have a sorted list of any objects of a class that has a compare to method, as you saw in the beginning of Java Interlude 5. Such classes implement the interface comparable. Since Java's wrapper classes such as integer and double implement the comparable interface, you can place instances of them into a sorted list. The first two methods are straightforward, but GetPosition deserves some comment. Given an entry in the sorted list, the method GetPosition returns the entry's position number within the list, as you would expect. We number the entries beginning with 1, just as we do for the ADT list. But what if the given entry is not in the sorted list? In this case, GetPosition returns a position number where the entry belongs in the list. The return number, if the return number is negative, however, the signal that the entry is not in the list. For example, if missed object is not in the sorted list S list, but belongs at position 3, slist.getPosition missing object would return a -3. Note that Getposition deals with an array list by returning -1 to indicate that any given entry belongs at position 1. The sorted list also has some, but not all, of the operations of the ADT list. We have already mentioned that adding an entry at a given position is not possible because otherwise the client would destroy the order of the sorted list. For the same reason, the list replace method is not available to a sorted list. The other operations of the ADT list, however, are useful for a sorted list as well, including the ones that retrieve or remove the entries at a given position. The methods getEntry and remove each have a position number as a parameter, but they will not alter the relative order of the entries in the sorted list. Although the list remove method returns the object removed from the list, it is not necessary for the sorted list remove method to do so. The client already knows at least the client already has at least a copy of this entry to enable it to invoke the sorted list remove. So here are some additional operations, and so those are fairly straightforward. And I'll just mention a couple of notes here that the ADT sorted list can add, remove, or locate an entry given the entry as an argument. The sorted list has several operations that are the same as ADT list operations, namely get entry, contains, remove, that is by position, clear, get length is empty, and to array. However, a sorted list will not let you add or replace an entry by position. And another note, the ADT sorted list orders its entries by comparing them. Thus, a discussion in the design decision in segment 719 of chapter 7, a sorted list cannot contain null entries. So here is the Java interface listing that specifies these operations in more detail. Note that the question mark super T, which 16J513 of Java Interlude 5 introduced, means any superclass of the generic type T. Here's just some more details, part 2. And in terms of a linked implementation, as all ADTs, you have a choice of several ways in which to implement the sorted list. You could store a sorted list entry in, for example, an array, a chain of list nodes, an instance of a vector, or an instance of an ADT list. In this chapter, we will consider a chain of linked nodes and an instance of an ADT list. Chapter 18 will use inheritance in the ADT list to develop a completely different implementation. So we have an outline of the class. An implementation that uses a chain of linked nodes to store the entries in a sorted list has several details in common with the linked implementation of the ADT list that you studied in chapter 12. In particular, it has the same data field, similar constructors, the same implementation for several of its methods, and the same definition of the interclass node. Thus, we outline in listing 17.2, shown on the slide, a class definition that implements the ADT sorted list. So let's talk about the method add. And so we'll show this figure, and then we'll have a little bit more details on locating the insertion point. Adding an entry to a sorted list requires that you find where in the list the new entry belongs. Since our assumption is that the entries are sorted into ascending order, you compare the new entries with the entries in the sorted list until you reach an entry that is not smaller than the new entry. Figure 17.1 depicts a chain of the linked nodes, each containing a name sorted alphabetically. The figure shows where the additional names Ali, Kathy, Luke, Sue, and Tom would be inserted into the chain, and the last comparisons that would have to occur to arrive at those locations. So here's an algorithm. Recall from segment 1210 of chapter 12 that you handle the addition of a new node to the beginning of a chain differently from addition at the other points in the chain. Adding the algorithm to the beginning is easy since first node references the first node in the chain. To add anywhere else, you need a reference to the node that will ultimately occur before the new node. Thus, while you traverse the chain of linked nodes to discover where the new entry belongs, you must retain a reference to the node prior to the one under consideration. A high-level algorithm that describes our strategy for a sorted list is shown here on this chart. Here's an iterative implementation of add. A Java implementation of the previous algorithm is shown. We use a private method get node before to search the chain for the node before the insertion point. Here we have the private method get node before. We still need to implement the private method get node before. We will need two references as we traverse the list. Clearly, we need a reference to the current node so we can compare its entry to the desired entry. But we also must retain a reference to the previous node because it is the reference that the method returns. In the implementation, these references are current node and before node. We still need to implement the private method get node before. We will need two references as we traverse a list. Clearly, we need a reference to the current node so we can compare its entry to the desired entry, but we also must retain a reference to the previous node because it is in this reference that the method returns. So in this implementation shown, these references are current node and before node. Figure 17.2 illustrates the logic needed to recursively add the names Luke to a sorted chain of names. Since Luke is greater than Bob, you recursively consider the subchain that begins at Jill. Luke is also greater than Jill, so you now consider the subchain beginning at Mike. Finally, Luke is less than Mike, so you make the actual addition at the beginning of the subchain that is before Mike. Adding to the beginning of the chain or subchain is the base case of this recursion. Happily, the beginning of the chain is the easiest place to make an addition. So for tracing addition to the list beginnings, suppose that that name list is the sorted list that the chain in figure 17.3a represents, as we're seeing here. Let's invoke name list add Allie to add Allie to this list. The addition will occur at the beginning of the chain. The public method add will call the private method add, and the invocation add Allie first node. The reference in the argument first node is copied to the parameter current node, and so it also references the first node in the chain as seen in figure 17.3b. Since Allie will be added to the beginning of the chain, the statement current node equals new node Allie, current node executes and creates a new node for Allie. This node is linked to the original chain as figure 17.3c shows. Notice that the first node is unchanged, even though it is the argument that corresponds to the parameter current node. The private method now returns the value of the current node, and the public method add assigns the value to first node. Thus, the chain with the completed action appears in figure 17.3d. In terms of a recursive implementation of add, the example in segment 920 displays the contents of a chain. Since that operation does not alter the chain, its recursive formulation was straightforward. Obviously, in our present situation, the method add does not alter the chain. Getting the recursive method to make these changes is a challenge in Java. Let's look at this recursive implementation of the method add before we describe why it works. You learned in segment 919 that you write a private method to perform the recursion, and you write a public method, typically the one that implements the ADT operation, to invoke this private method. Thus, we have the following method definitions that we're showing in this chart. For tracing in addition to the list interior, the recursive calls, what happens when the addition is not at the beginning of the original chain? Let's trace what happens when we add Luke to the chain in figure 17.4a. The public method add calls the private method add with the invocation add Luke first node, as in the previous segment. The reference in first node is copied to the parameter current node, and so it also references the first node in the chain, as figure 17a illustrates. Since Luke comes after Bob, another recursive call occurs, add Luke, current node dot get next node. The next argument in the reference to the chain second node, the one containing Jill. This reference is copied to the parameter current node, as figure 17b depicts. Luke comes after Jill, so the recursive process is repeated again, and current node references the chain's third node, Mike's node, as shown in figure 17.4c. Luke is less than Mike, so no recursive call occurs. We are at the base case. A new node is created and contains Luke and references Luke's node, as figure 17.4d illustrates. So since Luke comes after Bob, anyway, so that kind of walks us through that whole recursive process. And so we'll just continue on and finishing up here. So in terms of tracing the returns from the recursive method, having just created a new node, the private method adds returns a reference to it, as in figure 17.4d indicates, a statement that invokes add now resumes execution, node after equals add loop, comma, current node dot get next node. This node after is assigned a reference to the new node containing Luke, as figure 17.4e illustrates. At this point, current node references Jill's node as it indicated in part B of the figure. The next statement to execute is current node dot set next node after node. Thus, the data field next to Jill's node is changed to reference Luke's node as shown in figure 17.4f. The private method add now returns a reference to Jill's node. If we continue the trace, we will make Bob's node reference Jill's node, and first node reference Bob's node after Bob's node, even though these references are already in place. So let's just look at the efficiency of the linked algorithms. If you consider the analysis of the linked implementation of the ADT given in chapter 12, we will see that the performance of the add method depends on the efficiency of the method get node add. The later method locates the insertion point by traversing the chain of nodes. It is a big O and operation. The add method for the sorted list does its own traversal of the list to locate where to make the addition. The traversal is also big O N, making the addition to a sorted list a big O N operation. Figure 17.5 summarizes the performance of the sorted list operations. Deriving these results is left as an exercise. When comparing implementations, you should realize that the worst cases can occur under different circumstances. For example, a worst case addition to an array-based sorted list occurs at the list beginning, whereas for linked implementation occurs at the linked end. So let's talk about an implementation that uses the ADT list. As we noted in segment 17.17, the linked implementation of the ADT sorted list repeats much of the corresponding implementation of the ADT list. Can we avoid this duplication of effort and reuse portions of the list implementation? The answer to this question is yes, as you will soon see. You can certainly use ADT's list to create and maintain an alphabetical list of strings. It's natural then to consider using the ADT list when implementing the ADT sorted list. Basically, you can do this in one of two ways. Here we use a list as a data field within the class that implements the sorted list. Figure 17.6 shows an instance of such a sorted list. Recall from segment C.1 of Appendix C that this approach is called composition and illustrates that a relationship between two classes. Chapter 18 considers the second approach using inheritance to derive the sorted list from the list. Our class sorted list will implement the interface sorted list interface. We begin this class by declaring a list as a data field and defining a default constructor. We assume that a class LList has, as discussed in chapter 12, is an implementation of the interface list interface for the ADT list. Thus, our class begins as follows, as we're showing in this chart. So for the method add, the implementation of the operation of the ADT sorted list are brief, as the list does most of the work. To add a new entry to the sorted list, we first use the method getPosition, which is an operation of the sorted list. We assume that it is already implemented, even though we have not written it yet. Recall that getPosition finds the position of an existing entry within a sorted list, or the position at which we should insert a new entry that does not occur in the sorted list. The method sets the sign of the integer it returns to indicate whether the entry exists in the list already. When adding an entry to a sorted list that can contain duplicate entries, it does not matter whether the entry exists in the sorted list already. Thus, we can ignore the sign of the integer that getPosition returns. Notice that the following implementation includes a method abs of the class math to discard the sign. It also uses add operation of the ADT list. So in this section, calls to ADT list operations are highlighted. For the method remove, we also use GetPosition when removing an object from a sorted list. This time, however, we do need to know whether the given entry exists in the sorted list. If it does not exist, we cannot remove it. In such case, remove returns false. Also notice that the method uses the operation remove of the ADT list to make the deletion. Thus, the method has the following implementation shown in this slide. For the logic GetPosition, implementing GetPosition is somewhat harder than implementing the previous two methods. To decide where in the list an entry is or belongs, we need to compare an entry to the entries already in the list, beginning with the first one. If an entry is in the list, we obviously compare entries until we find a match. However, if an entry is not in the list, we want to stop the search at the point where it belongs in the sorted list. We take advantage of the sorted order of the objects by using logic similar to that described in segment 17.8. For example, suppose that the sorted list contains the four names Brenda, Carlos, Sarah, and Tom. If we want to see whether Jamie belongs in the sorted list, we discover that as strings, Jamie is greater than Brenda, Jamie is greater than Carlos, Jamie is smaller than Sarah. Thus, Jamie belongs after Carlos, but before Sarah. That is at position 3 in the sorted list, as figure 17.7 illustrates. To compare an entry to an entry in the sorted list, we first use the list operation getEntry to return the entry at the given position within the sorted list. Then the expression an entry dot compare to list dot getEntry position makes the comparison. So here is the implementation of GetPosition. And so in this following implementation, the while loop finds an entry position in the sorted list, and the if statement sees whether an entry is in the list. And so let's just finish up with some comparisons here for the efficiency of GetPosition. As an example, as we examine GetPosition as given in segment 17.21, we note that the list method getLength is a big O notation big O notation 1 operation. Therefore, we need not be concerned with it. On the other hand, a loop examines the entries in the list one at a time by invoking getEntry until the desired entry is located. Thus, the efficiency of GetPosition depends on part of the efficiency of getEntry. However, the efficiency of getEntry depends upon which implementation of the ADT list you use. We will examine two list implementations that lead to rather different efficiencies for GetPosition. Chapter 12 discussed the efficiency of the ADT list operation. Figure 17.8 recalls the worst case performance of the list operation that we need to complete our analysis of the sorted list. If you use an entry to represent the entries in the list, getEntry is always a big O notation 1 operation. The loop in GetPosition is therefore big O notation n in the worst case, and so GetPosition is big O notation n when the list has an array-based implementation. If you use a chain of linked nodes to contain the entries in the list, the method getEntry is big O n notation n. Since GetPosition's loop invokes a getEntry, we see that GetPosition is big O notation n squared in the worst case. Each time getEntry retrieves the next entry in the list, it starts its search at the beginning of the chain. This fact is the cause of Getposition's inefficiency. So figure 17 summarizes efficiency of the sorted list operations for array-based and linked implementations of the ADT list. Confirmation of these results is left as an exercise. You can see the implementation of the sorted list given in this section is easy to write, but is not very efficient if the underlying list uses a chain of linked nodes. Chapter 18 will show you how you can reuse the ADT list in the implementation of the sorted list without sacrificing efficiency. Okay, that's it for our lecture. Thank you very much.